In the early 1960s, surfing meant the search for the perfect wave. Mail was something delivered by the post office. Online meant waiting behind someone at the cinema. And a server was the waitress at your favorite cafe.
Oh, I'll take your order. Make mine a ham sandwich and coffee.
But in the world of computers, the new idea was something called time sharing.
The old computers had been big machines that you punched cards and you submitted the cards in decks, and the next day you got the answers. But in '69, time sharing was happening, where you would actually sit at a terminal and you would type in your questions and your programs, and the answer would come back 2 seconds later. If you were very avant-garde, you had a terminal in your house and you were logging into a computer across town.
In 1966, Bob Taylor from the Advanced Research Projects Agency needed a separate terminal to log into each of several time-shared computers at research centers across the country. No two computers could talk to each other, so Taylor had to move from terminal to work on a different computer. If all the computers were part of a common network, he knew that just a single terminal would be sufficient.
Taylor wanted to build a network because he thought it was crazy that he had to have 3 different terminals to talk to 3 different machines instead of one terminal that could talk to all 3. So his notion was to pursue the creation of a network which would link heterogeneous computers to each other through this network.
Taylor asked for money to build a computer network, arguing that it would save the agency time, money, and resources.
It was a very straightforward connect researchers to expensive computers that you would not want to replicate. Resource sharing was the term.
Taylor was allocated $1 million to turn his theory into the reality that would eventually change the way we live.
We all knew that we were dealing with very powerful technology. But I don't think any of us 20 years ago or 25 years ago had any appreciation for what it would be like if, you know, everybody on the planet had access to information or could produce information and share it.
Taylor recruited Larry Roberts for the job. Roberts had built the world's first experimental connection between 2 computers at the Massachusetts Institute of Technology.
I knew that I knew how to do it because I actually had built the first network. I had lived with Len Kleinrock at MIT and learned about packet switching and queuing because he was my office mate. And so I had built the connection between the 2 computers as basically the same kind of connection ARPANET had, except that now we were going to distribute it to more people.
Roberts wasn't sure about the best way to network mainframe computers. One way would be to link them in a chain. But this design had a flaw.
If you tried to interconnect the large computers directly, then each of those large computers would have to figure out how to work with each of the other large computers. So they would have a tremendous problem in their software to be able to figure out the rules and procedures and protocols for dealing with 10 different kinds of computers out in the country.
On a taxi ride home from a conference, Roberts came up with a better way to connect the computers when a fellow engineer suggested building identical, special-purpose mini-computers to form the network and tie each time-shared computer to one of them.
This way, they only had to learn how to deal with the one little computer that you put there.
It was a brilliant simplification, and it made the universities more willing to participate in the network because it wouldn't interfere with their own computer projects. On paper, Roberts had the network design worked out. Now all he had to do was find someone to build it, but he knew who it wouldn't be.
The phone companies, A, believed it couldn't be done, B, didn't think it would be useful or anybody would want it if it were done, and C, had huge investments in their current communication systems and weren't interested.
If there was going to be a computer network, someone else had to build it. But who? Back in 1968, communication technology meant typewriters, not word processors, pounded out letters. Most telephones used rotary dials. Television was black and white, not color. The height of high-tech was the lunar module, which had less computing power than today's personal computer.
That may have seemed like a very long
1968 was also the year Larry Roberts sought out the engineers to build the Advanced Research Projects Agency's computer network, the ARPANET, the acorn that would grow to become the Internet. It was going to be based on special-purpose mini-computers called Interface Message Processors, or IMPs, and a revolutionary technology called packet switching.
So here's the way it works. Suppose I want to send a long document. I feed it into the network. The first thing the network does is chop that up into a lot of little pieces called packets. And each packet is launched into the network, and it tries to find its way to its destination, each packet operating independently. At the other end, the final destination takes all these packets, think of them as little postcards carrying your data, puts them back into a long document, and delivers them to the recipient at the other end.
The plan was to network 4 identical IMPs. Each one was to be attached to a different kind of mainframe computer. A Sigma 7 at UCLA, an SDS 940 at the Stanford Research Institute, an IBM 36075 at the University of California at Santa Barbara, and a PDP-10 at the University of Utah. Roberts asked 140 companies, including AT&T and IBM, to bid on the project. But the giants of communication refused.
No, they didn't think it would work. They didn't see that it was very important or mainstream. I mean, after all, communications, well, we've got our own communication systems here at IBM, and AT&T does the telephone system. What else do we need? What's your problem?
So the telecom guys would say, little boy, go away. You represent no revenue to us. And they were right, we didn't. So little boy went away and created packet switching on its own.
A small company, Bolt, Beranek and Newman, known as BBM, wasn't sure either. But they were willing to try. Frank Hart headed their team.
Well, we had to, first of all, figure out if we knew how to do it. I think it was a relatively revolutionary concept to put together a packet switching communication system, and no one had done that before.
BBN won the contract and went to work, building the IMPs for the ARPANET on January the 1st, 1969. The first was due at UCLA in 9 months. Hart's team was faced with a number of obstacles and very little time.
It's not like a scientific discovery of the second law of thermodynamics or finding what DNA molecules look like. It was an engineering problem with dozens of very difficult, messy, undone engineering problems. And some of them were simply the fact that it was such a rush schedule.
UCLA was also under a deadline to write the software so its Sigma 7 computer could communicate with the IMP. A group of graduate students was chosen to forge this first important link in the world's first computer network.
The senior professors who were in charge of each of the projects, the principal investigators they call, really did not spend much time thinking about or focusing on it. It was left to the next tier down, to the graduate students or in some cases staff members at places like SRI. Just figure out something useful to do with this.
It was Steve Crocker who wrote the code to join UCLA's computer to the first IMP in what was to become the ARPANET.
The idea of having one computer send a program over to another computer was a big leap in some ways, but very natural in other ways. But in those days, there was no commonality across the computers, and so part of what we had to think about was in order to make that idea work, there would have to be a common language, and we actually spent time trying to define what that language might be.
Back at BBN, Hart's team was facing numerous engineering challenges. How are the packets prevented from circulating forever? How do they know when to stop at their destination?
You dump a piece of message into the system, and now it's to wend its way through it, at each node picking the best path. Well, what stops it from circulating forever? That was a very difficult technical problem. No one had done that. Another thing, a host has a big message to send. It dumps the big message in. What stops it from overflowing? What protects the system from just having the stuff fall on the floor?
There was also concern about the phone lines. They were built for voice traffic, not data. Special hardware and software had to be built so that when errors occurred, the IMPs could retransmit the message. And there was no guarantee that the mainframe computers would even hold up. They were simply not built to run non-stop as communication machines. So how would the team know where the problems were occurring in order to fix them?
When some guy in some site hit a key on his keyboard, the message had to go from his keyboard to his big computer, from his big computer to the little computer, through a whole bunch of other little imps at other sites, and finally to a one at the destination, and then into the host, and then it had to come back all the way. And when the guy didn't get an answer, he didn't care where it broke, he just didn't like it. He kicked it, you know, he would yell and scream. So you had to have a way of finding out where it broke. And that was, again, a difficult problem for the network authority, which was us in this case.
There were problems right up until the day BBN shipped the first imp to UCLA.
I mean, there were people in the group that wanted it perfect, and there were other people that said, come on, we got to get it out of here in 9 months. It has to be just good enough. That was a kind of decision that I ended up having to make. What was good enough, and where did one seek more perfection?
On September the 1st, 1969, the first piece of hardware created for the computer network that was the forerunner of today's internet arrived at UCLA.
What I do remember is that they slid the thing in place, turned the power on, and the lights immediately started blinking because the program had been put in when it left, before it left BB&N, and it was just turned off. When they turned it on again, it picked up right where it left off. Now, there wasn't much of a network to speak of. I mean, there was the first node at UCLA. We didn't have anybody to talk to, so we just sent traffic to ourselves.
By the end of 1969, all 4 sites were interconnected. Had this primitive computer network failed, the effort to network computers might have been dismissed as just another project beyond the reach of current technology. But it worked. In April 1971, the ARPANET had 18 mainframe computers hooked into the network. Robert Metcalf was a graduate student at the Massachusetts Institute of Technology.
The thrill was connecting things together. You know, there's action at a distance. How, you know, you can wiggle something here and it moves over there. So I was able to form packets of bits and send them. And over the phone, the guy in California would say, I got it. And I'd say, well, send it back. And then he'd send it back. And it was the thrill of reaching out and touching someone or something far away.
At first, there wasn't much to do on the ARPANET beyond transferring data files among its members. But then a new capability was added, the first killer application that would harness the masses and take computer networking to a new level: email.
I was actually working on a mail program, but it was a program for a single computer so that you could send messages from yourself to another user on the same time-sharing computer. And I had written a couple of programs to transfer files, and it occurred to me that since the mailbox that I was sending these messages to was nothing more than a file, I could send that file across the network instead of keeping it within the same machine. And so I put 2 programs together, modified the code a little bit, and the first email program was created.
Tomlinson did much, much more than just write the code for email. With one keystroke, he gave the world a new icon for the information age: the @ sign.
The @ sign was the most obvious choice because we're talking about a user who was at some computer, and it just made sense.
What has become one of the most popular applications on the internet was a program Tomlinson devised in his own time.
It seemed like a neat idea. Nobody was clamoring for email. I mean, there was nobody, our sponsor, Department of Defense, didn't say anything about wanting email. My boss didn't say anything about email. But in fact, nobody said anything about email because the term wasn't coined until several years later. But it just seemed like an interesting thing to do with a computer and a network. And so I just did it.
So then electronic mail became the completely unanticipated killer app, as we say, for the ARPANET. We went from remote login, file transfer, electronic mail in a year flat or 2 years flat. And then it stayed that way for 20 years.
There were 3 other developments: the transistor at the end of the 40s, the floppy disk in the 70s, and the Intel chip. I think They brought computing down to what we all understand to be in our homes. On top of that, email clearly is a killer application. There's no question about that.